I'm using PuTTY so I don't get pretty graphics. So this is the first part of the auto grader. The first part of the auto grader is just to check to see whether or not you typed in an actual assignment. So for example, did you type in assignment 1? Did you type in assignment 2? Which one did you type in? Otherwise the assignment is not found. You'll notice that your name and your mask come from a file called student name and student mask. That's inside of your home directories there. Hopefully I didn't clobber those the other day when I screwed up the... If you didn't notice yesterday, the assignment 2 stopped working entirely. That's because I clobbered a bunch of shit on accident, and hopefully I didn't clobber all the student names and student masks on accident. So if I did, I'll fix those later, but for now it's okay. You'll notice here, for example, if there isn't an argument, this is how you ask for an argument right there. It's kind of weird, I know Bash is strange, but that's how you ask for the number of arguments that were passed to the program. If the number of arguments does not equal 1, then you have to enter the assignment number. If the assignment is equal to the number 1, then it grades it using the grade assignment of grade 1, and then otherwise it uses grade 2. Pretty straightforward. Let's actually take a look at grade 2, or grade 1, because grade 1 is a little bit more interesting than grade 2. Grade 1 essentially takes your first 2 arguments as your name and your mask account and your name. And then it finds the turn-in directory, which is going to be your local directory, and hand in assignment 1 for assignment 1. Those are all the files that we're going to be looking for, prog 1, 2, 3. This command, this dir command, it's a command that gets the location of this script. That allows me to use a timeout, which does the parts that will time your program out if it tries to open a loop, which is a problem. When you're grading when we're grading, essentially I say for every file in program 1, program 2, and program 3. So that creates a set of 3 file names, which are those 3 files, and I do this loop. This loop should look relatively familiar if you've done the second or third parts of the assignment. You should have a loop that is something similar to that. You might have a different thing on the right over here to be able to get all the file names. I'm just hard coding it because I want to only look at specific file names. This line, this if statement here, is this bang, this not symbol says not file exist. So this first thing, if the file does not exist, fail. With an exit 1 instead of an exit 0, otherwise the file succeeds. The compile time checks, you should also have something similar. You don't necessarily have to for part 3 of this assignment. You have some sort of GCC. This file name command, this thing here, is this. So like when we have prog1_1.c, it takes this and takes the dot and it removes the C off of it. So you only get the file name without the extension. Then I do a GCC, and I changed this recently so that instead of putting it into, maybe this is the local directory. I don't remember. I think it's the local directory. Putting it in the local directory instead of turn-in, but it compiles the turn-in file and then checks the return code from the compiled file. Maybe I shouldn't want to do that. I'll have to check that again. Anyways, it works for the other side of the algorithm that I did. Yes.
For 2-1, I don't know if it's submitting an argument correctly.
Okay, I'll fix that too. For the runtime checks, I'm doing the same thing. I essentially run the timeout command, and then I run your program with the timeout. A 2-second timeout. I echo the number 30 into each one of them. And then I check to see whether or not your program returns 0. If your program doesn't return 0, it will fail. It's either infinite looping or failing. And that's essentially all the autograder does. It's very basic. It's pretty dumb, this version of it. I worked with Caleb yesterday to make a better version for automatically grading it. So it puts in a value, and it's how do you get the value that it comes back out of it. I'll fix that after class for grader 2. In the what was it? So in the assignment, what is assignment 2 all about? What's the thing that I wanted you to learn?
How to properly use Google?
It's a big part of it, yeah. What was the besides how to Google things? What was the thing I wanted you to learn about programming and about the system that we're working on? What tool did we use the most? grep. So I wanted you to learn how to use grep because grep is very powerful. What's another thing I wanted you to learn? Cat? Okay. You can actually do the entire sentence without cat at all. Oh, huh?
Cut.
Cut, yes, cut. Using cut isn't really cut is useful, but it isn't the command that I specifically wanted you to learn. The thing that I really wanted you to learn was the pipe. So the pipe between the grep and the cut. The other thing I wanted you to learn was when you're doing echo, for example, when you have echoes, you can echo parts of file names with dollar signs, and you can stick them together. How do you make a dollar? Like, if you have a name, how do you add a .c to the end of it? Those kind of questions. If you wanted to have 2 lines of responses, you have to echo twice. What if you wanted 1 line, if you only had to echo once? You have to echo all of the commands? Can you run other commands? How do you get different kinds of information? How do you duplicate the parts? Secondary to that, I wanted you to be able to learn how the hell do you make files on Rohan. How do I open up and make a shell script? Oh, I opened up NEdit, I was able to save that shell script. If you weren't able to do that, because there was a number of students that didn't know how to do that in the beginning, and you're able to say, I need to make a new shell script, and you're able to start that and do it now, that was like 30% of the assignment. Then how did you learn that you could run the same command on the command line as you could type into your file? Most people didn't know that before this assignment started. And hopefully now you know that. You know that you can run the command in your console, look and see what it's doing, and then stick it inside of your script. That was really what a lot of these things were about for this assignment. Not necessarily like, oh my god, learn all these bash commands. Really what it is how do you go about using a Unix computer? How do you go about automating tasks? How do you go about this kind of process? That's really what a lot of it does.
Is there any sort of version of that? How you said you can type in for a bash script, we could just type it into bash. Is there any version of that for C? Like how Python has IPython?
So not for C. So for that maybe there might be one, but I don't know about for C. I know for Python, the default version of Python is the interactive shell. That's how Python was started. Almost all interpreted languages are interactive by default. That's just a lot of the way that they work. So we will use Python in this class, and Python is interactive, and we will have an interactive shell for Python. So for example, in Python, if you just come into the command console and you just type in Python, now we have this. You can't see that, down there. I mean, that would help. This is the Python terminal here. Stealing the chip. Okay. This is a Python terminal down right here. So if I go in and type in here, I can type a equals 3. And now I have the variable a, and it equals the value 3 in Python. And even if I type something that doesn't make any sense in Python, said, that's invalid syntax, I can still ask it to, I believe it's print. Print a. A is still the value of 3. Right? So this is that part of it's the interactive shell. So this is the interactive shell for Python. When we're not in Python, this is the interactive shell for Bash. I can type here. Sometimes things don't work. Command not found. Very similar. We'll also, so the fifth assignment, sixth assignment, I believe, is implementing an interactive shell for Lua. So Lua doesn't, by default, there isn't a Lua command. I can't come up here and say, hey, run Lua. Lua isn't by default installed on Rohan, and so we can type Python and get the Python shell. Lua isn't a default shell. So the first assignment that we're going to deal with doing with Lua is how do you make an interactive shell? Okay. Any other questions about this? Or about the assignment? And other stuff? Yes?
For the third section, what kind of arguments we expect for the four?
The 4 file names. It should just be the name.c. So I don't remember what the names are, the files are, but it's like T87GF.c. Right? So your program will be executed like this. .c with the 4.c files executed. And this is program 2.3 is assuming that program 2.2 has successfully copied them to your local. To the directory that this command will be running. Okay? All right, good questions. All right, the other thing we're going to talk about a little bit today is we're going to let's look at some terms that get tossed around a lot that we don't necessarily know what they mean. So, for example, what does it mean? Erase this for now. What does this mean to code? What does it mean to code? And I say, hey, let's go code something. What does that mean? What do you guys think it means?
Implement the logic from your program if you've already the program.
Right?
Yeah.
Implement a solution to a problem. Implement a solution to a problem. Right? That's the implement the does coding have anything to do with solving the problem?
Nope.
Will you have to solve problems while you code? Yes. But coding itself is not the act of solving the problem. Coding is just the implementation of the problem. So we're talking about coders or coding and things like that. Coding is the easiest of all the things that we have to face. 107, 108, 237, you have been asked to do very little programming. Almost only coding is the only thing that you've been asked to do. One of the reasons why this assignment might have felt very difficult is that this assignment is the first assignment where I asked you to do multiple things. I asked you to do more than just code. I asked you to do another step on top of that. What's the step above coding? Programming. And what is programming then? Hang loose this up.
Solving the problem?
Solving problems. Solving problems. I asked you to solve a number of problems without telling you what tools to use. Does that mean that I'm going to get a lot of different solutions?
Yes.
Yes. Because the art of programming is determining what are the best tools to use. Of the tools you have, what tools can you use to solve the problem? Some people will have awful solutions, some people will have awesome solutions. I don't particularly care for this assignment. I don't care if your solution is horrible. If you have the worst solution possible and it works, I'm okay with that. Right? Really, I'm okay with that. Because what you've done is you've taken the tools that you know about, used Google to learn about more tools to solve a problem, and that's the art of programming. Okay? What's above programming? So the problem is going to be here. We'll call this instead of problem, let's call this the let's call it objective. Thank you. Now, sometimes if the objective is narrowly enough defined, essentially you just code a solution to it because there isn't any problem solving to be done. Sometimes you just have to program a little bit to find out the solution to that objective. But there's a step in the middle here, or a couple of steps, depending on how you think about it, that's important as well. So the objective is what you want to do. well, not necessarily even you, what wants to be done? Kind of thinks that the thing that's being done is the thing that wants it. Who decides what wants to be done? Whoever is in charge is usually the answer, and really the answer comes down to, unless you're working for yourself for free, it's whoever has the money, is ultimately comes down to it. When you're working for yourself for free, you can choose the objective. If you're working for somebody else for free, they get to choose the objective because you're just not charging them for it. If you're working for somebody else for money, they choose the objective and tell you what to do. What's this middle step? There's couples in here. I'm just going to label one of them. Software what? Starts with an E. Engineering. What is software engineering? How do we go from that to this?
We have to choose which language that we're going to be
That's part of it, but it's even that's part of that's kind of the step between software engineering and programming.
Managing our resources.
That's software management or project management. That's not even necessarily, you're right about that, but that's not necessarily specifically a software problem. And engineering is really the term here that tips us off, because when I talk about the engineering in this sense, I'm talking about engineering in all fields. If we're talking about building a bridge, as an example. The objective is I want a bridge across the 8. There's a huge engineering problem before I can even start pouring concrete. What is this engineering problem? You're right, I do have to build frames. Before I can even build the frame, that's still down here in the code. So design, what does that mean? What does it mean to design the bridge? What does it mean to create a blueprint? Yeah, so the thing that we're doing here is we're discovering all of the problems. Find all the problems that need to be solved. So really, the only thing that's harder than solving the problems, and sometimes solving the problems is the hardest step, but typically the harder thing than solving the problems is discovering what problems you need to solve. And I asked you to do some of this in this first assignment. When you get very little information about what you're doing, and you don't know a lot about the environment that you're working in, you have to find what problems you're going to face. And this is a really hard step. If you're not familiar with it, you're not familiar with how to go about software engineering or finding problems in the first place, this is going to be a hard step for you guys. So I asked you to do a little bit of these 2 steps up here instead of just code and program. So I asked you to move from this level to this level, right? One of the things that we're going to do on the midterm is there's going to be a little bit of this software engineering step on the midterm. And the way that we're going to get to the software engineering step on the midterm is I'm going to tell you what needs to happen. I'm going to tell you what the objective, what I want to have done, but I'm not going to tell you how I want you to do it. You know nothing about any of these steps. So what you have to do is you have to figure out, they're relatively simple. Don't worry about it. They're relatively simple. What are all the problems that are present? Once you know the problems that are part of that are present in that objective, then you can choose a language. After you know what problems there are, then you can choose a language. Or a framework, or a set of languages, or a lot of other things. And until you're able to determine problems, so for example, if I asked on the midterm, if I said, hey, write some code that calculates the Fibonacci to the 3,000th number, 3,000th Fibonacci number. If you sat there and you go, I'm going to write this in Bash, and okay, go for it, right? But when you've chosen Bash, essentially what you told me is that you haven't discovered what the problem is. If instead I say, hey, Go tell me all the files that contain the word hello in them. And you choose C. You've chosen the wrong language. We haven't determined what the problem is. So for example, what's the difference between finding so what is the problems when we're thinking about software engineering for calculating the Fibonacci number?
A language can hold that many.
So languages that can hold big numbers, because the Fibonacci numbers get big and they get fast and they want to do recursion, or maybe not a recursion, maybe something like that. So what languages do that? We have this big numbers with some sort of large math component to it. We already know, and then when we go math component, big numbers. Bash doesn't do either of those things very well. C does, maybe not big numbers. Java does really well with those things. Maybe Java's even the best answer. And then for the second problem, we said find some text strings. Is C good at text problems? No. Is Bash good at text problems? Yeah. That's where we go, oh, that's how we choose the language. One of them is a string problem, one of them is a math problem, and each of those problems have a solution or a particular language that is good. Some languages are better at more things than others. One of the reasons why everybody likes Python is because Python is good at both things. It's good at math and it's good at string manipulation. And its syntax doesn't suck like Bash. So, there's that. Any questions about this here? This is something to keep in mind as we're going through this course. One of the things I want you guys to think about is, why are we learning this language? What is the purpose? What niche does this language fill? What does this language solve? How do you? And then later you can say, when would I want to use it? Is this anybody's water? No? I'm just going to put it on the floor. Okay. Tuesday, we started talking about pointers in C. Today, we're going to talk about dynamic memory allocation in C. What's dynamic memory allocation? Changing gears. Yeah, but that's not exactly what this word means. Memory is always allocated at runtime. It's still true. So, yes, but no. You're right, but no. That's not what this means. That's also true. That's good. Dynamic means varying. Memory allocation means amount of. So we know what these words mean. If we're not talking about dynamic memory allocation, what kind of memory allocation are we talking about? Static? So what would static memory allocation be? Sorry? Unchanging. It's not necessarily unchanging. I guess you could say the allocation is unchanging. Oftentimes static memory allocation is unchanging, but it's, and we'll talk about why dynamic memory, why this is a weird kind of question. Static memory allocation is memory that is allocated inside of the executable. When we say that it's allocated inside of the executable, does anyone know what that means? Does that not make any sense? All right, I'm going to pull this board out and we'll make it lighter. If this is our RAM, here, usually we're going to take a section of this RAM, and the section of this RAM is going to be identified as code. So when we say code, we mean this is where the compiled code or the execution code, the code that is part of the program, is executing or that will be executed inside of the RAM space. We say static memory allocation. Usually we mean that the allocation is made inside of this portion here. So if I, for example, allocate a single static variable, I will have one single static variable allocated here. When we see the static keyword for things like in Java and even for things inside of C and stuff like that, it doesn't mean that the value doesn't change. What does it mean when it says static in Java or static in C?
Kind of global, able to be accessed by more than just.
Global's not correct. It's not about the access. Because the public, you can have private static things. So if this is a static thing, how many do I have? One. Can I make more of those once the program started? The answer is no, I can't. So when we talk about static things, it means that there's a finite number and they've already been allocated when the program starts. So in Java, when you talk about a static member variable or a static variable, that variable exists from the beginning of the code execution, and the number of them will never change. You always have that one static variable. And it's allocated inside this code section. Now there's two other places that we allocate memory. Fortunately, there's two other places on the graph here. What do we got? So we have the stack. Which grows up. The stack is not, while it is dynamic, we don't call the stack the dynamic memory allocation. The stack is where well, I'm not going to say, what is the stack for? What do we allocate there?
Can we save the state of the program?
That's true. You have the right words, but I want you to be, so instead of the 237 level, I want you to be at the C level. Let's go up one level higher. The function, so it's about function calls, but the function what? The function variables. So the stack, we save the function variables. All the variables for all the functions. As we call functions or methods more and more, our stack will grow and we're saving the state of the previous functions. That's what you were talking about. So as we call more functions, the stack grows. As the functions finish, the stack will shrink back down. And this is where we put all of the function variables. Let's look at an example for this. Erase this one. So I've written this function foo, and I've written this function main. It doesn't do anything useful, really. So the function foo has a single parameter x. It has a single a single function variable y. And then we have the function main, and it has a single function variable x. And then it calls the function foo with x inside of it. When we do this, when we have this code on the board here, main starts. Main is where, when a program gets instantiated or created, when a program gets created by the operating system, it starts at main, that's our entry point. We have defined a single x. That single x is going to be placed on the stack. So we talk about that x. being on the stack here. That x will be on that stack. We'll assign that variable to 3, and so that value will have 3 on that stack. When main calls foo, the foo function, we can talk about like the foo function comes alive is one way you can think about it. The foo function is born. When the foo function is born, the stack grows up. It means more space is allocated on the stack, and all of the variables that are part of the foo function are put on the stack. How many variables are for that foo function? 2. What are those 2? X and Y. One for the parameter x, one for the variable y. So we have x and y. Y will get the value of 7. X will get the value of 3 because when we call it with the value down there. We have 2 copies of x. We have 1 copy of y. The x and the y that are on the top of the stack are for this function foo, and the x on the bottom is for that main down there. That's what the stack is for. This is not what we call dynamic memory allocation. The reason why we don't call it dynamic memory allocation is that when the program starts, we know how much memory is going to be allocated for each function. How much memory is going to be allocated for foo on a 32-bit machine every time I call it? How many bytes? So I go, how many variables do I have? 2, right? What are those variable types? Integers. How big is an integer on a 32-bit machine? How big is an integer on a 32-bit machine? 4 bytes. Right. So just say it a little bit louder. Sometimes I don't hear you very well. 4 bytes. So 2 times 4 is 8. So we know that it doesn't matter when or where I call foo. When foo is allocated or called, 8 bytes will be allocated on the stack. Every single time. How many bytes are allocated on the stack when I call main? 4, because I have that single integer that's 4 bytes wide. So I know that automatically. The stack does grow and diminish, but it's not dynamic in the sense that with a dynamic allocation, I don't know prior to the start of the program execution how many bytes are going to be allocated. So really when we talk about dynamic memory allocation, we're talking about memory allocation on the heap. Memory allocation on the heap. When does this happen in Java? What's your time? Yeah. So I'm sure there's enough chairs. All right. In Java, how do we do dynamic memory allocation? I know you guys have used it. You just might not know that's what you're doing. Go for it. Okay, so what is that keyword? New. In Java, every time you see the new keyword, you're doing a dynamic memory allocation. That new keyword is doing the new keyword actually is what we're going to talk about. It's the malloc instruction in C, which is what we're going to talk about here in just a second. The new keyword allocates the memory. The constructor then builds that or fills that memory with the correct values. You don't necessarily know how big it is as a programmer, however, the compiler does know how big each one of those objects or each one of those things that are going to be created are going to be. C does not have objects. C doesn't know how much space you want to allocate when you're trying to allocate memory. You have to explicitly tell C in bytes how much memory to allocate. So if you don't know, you have to find out. This is both a part of getting more control and having having more responsibility. Yes?
About the memory allocation, what would stack be considered the other things?
I don't know the technical term of that. Let me think about that. I'll talk to you about that later. Let me find out and I'll get back to you. Good question. It might still be called dynamic memory allocation in that case versus static. Just because But I don't consider it dynamic because we know it before. Dynamic, we're usually always talking about. Technically, they might be both dynamic, but in standard usage, if you're talking about dynamic memory out, you're talking about the heap. All right. In C, the way we allocate memory dynamically is with a malloc call. There's several calls. There's malloc, there's alloc, there's realloc. Can't think of anything else off the top of my head. There's more. There's more calloc. And some others. I'm going to write those on the board so you know those exist, and then I'm going to erase them because you don't ever want to think about those. Realloc is the only one that might be useful. However, on older machines and on smaller memory machines, machines with less RAM, it almost always fails. So just don't do it. Is the answer. Malloc is pretty much, I don't know about today, but in the past, malloc was the only really safe memory allocation technique. Memory allocation is what it stands for. It's a function. What you do is inside of this function, you pass the number of bytes that you want it to allocate. Pass the number of bytes you want to allocate. The return value for malloc is a void star. Is the return value. For C. What does the star mean?
Reference?
It's a reference. It's a pointer, right? What does void mean? No type. It's a pointer to something that has no type. Why? Correct. In C, C doesn't care what you're allocating memory for. C's like, you want how many bytes of memory? You give it, I want 7,000 bytes. It gives you 7. Here you go. Here's a pointer to 7,000 bytes. I literally have no idea what you're using it for. The C compiler and C programs don't know. So when you do this malloc command, who's responsible for knowing what point that's pointing at? The programmer is. By the same token, I can say, hey, give me 7,001 bytes. I don't know what the hell I'm putting there, but I can allocate however much or however little I want. I can allocate 1 byte at a time. In Java, when you say new, do you know how many bytes you're allocating? You have no idea. New allocates however much it thinks it's going to need. Java is notorious for being a memory hog. It just allocates way more memory than it requires. Part of that is that the Java virtual machine just goes, I think I'm going to need 8 bytes for this. I think I'm going to need 42 bytes for this. Maybe 1,000 for that one. I don't know. It just kind of guesses for a lot of things and just over-allocates memory. With C, you get very tight memory constraints. Let's suppose you're writing a program in C for something like, I just noticed we had a robotics class going on the 4th floor. And they're running these little robots, and they have this little microprocessor that has like 4 kilobytes of RAM on it. That's 4,086, whatever this number of bytes of RAM in there. You can't allocate a megabyte of RAM because it doesn't exist on that system. You can't run Java on that system because there's not enough RAM to run the virtual machine on it. You want to be able to allocate 12 integers, you have to make sure you're allocating 12 integers. You want to allocate 12 words instead of 12 integers, you can allocate 12 words with malloc. And then you get to decide how big everything gets to be. So you have lots of control over your memory, but the compiler doesn't help you. So to start with, what I want you to do, let's write a program. Let's write a main program that the way you did before. So for assignment 1, that takes in the user's name. Start by writing that program. I'm going to write it on the board. I want you guys to think about how you did that, how you declared the array, and how you did the scanf. We're going to look at how we're going to do the same exact problem with a dynamically allocated memory versus the statically allocated memory. I made it shorter than it was before. That's basically most of it, correct? How do I fill the rest of this out? So I do the char, the buff, with the 256 here. What does all that mean? Allocate 256 bytes as an array of characters, correct? Where does that memory get allocated in our picture here? On the stack. When you look at this, what is buff? It's a variable. It's a function variable, right? So that means since it's a function variable, it's going to be allocated on the stack up here. And so we're going to get 256 bytes for buff allocated on top of that. That's going to be allocated on the stack. What happens when main finishes? Besides the fact that the program terminates. What happens when a function finishes to the stack? Say it, you say it. Right, so it's removed from the stack. And so the buff that we allocated when main gets called, when main gets started, when main finishes, that buff is removed from the stack. That's where the stack grows and shrinks. And if you haven't taken 237 yet, you're going to learn about this in, I don't know, another 10 weeks, 8 weeks. So the stack will grow up and down. When main is called, that memory is allocated on the stack. When a function finishes, the memory is deallocated. Dynamic memory allocation doesn't get allocated on the stack. But we do need a similar part. So I'm also going to declare a char. I'm just going to write it underneath. And I'm going to declare this, let's call this, give me a name. What do you call it? Monkey? Okay. Char monkey. When I declare that as char monkey, where does that char monkey get declared? Nope. What is that monkey? It's a character, but it's also a function variable. Where does it get allocated?
Stack.
On the stack. So now with those two allocations, I get the buff, which is here. And how much memory do I allocate for that character? One what? 1 byte. Why do I get 1 byte in C? Because a character is an ASCII byte, right? What if I allocated a character in Java? How many bytes would I allocate? 2, because it's a Unicode character, right? This is one of those things where are we on the abstraction layer? Do we care really that it's a byte? And for this problem, we do, but in general. So we get this single byte here for, what do I call this? Monkey. It's called ham. Is that enough space for me to write my name? No. What do I need then? Instead of one single character monkey, what do I need? What did I say we were going to do? We're going to do some memory allocation. That means that we're going to come down here to the bottom. We're going to be like, yeah, give me some space down there. So what I'm going to do is I'm going to give her that scanf so I can write the allocation. And then we're going to look at that monkey again. We're going to see how we're going to fix that monkey. So let's go and do the memory allocation. Let's say, let me write this part of the right here. Malloc. How many bytes do I want? How many bytes do I want? 256, that's a good number. Boom. When I do this malloc, just assume that I have this scanf afterwards still. Write this scanf. When I do that malloc, when that malloc executes, I get 256 bytes down in my heap down here. Do I know where that is? No clue. What am I trying to do to it? I'm pointing at it, right? If I'm trying to point at that memory allocation, that memory spot, that's how I know where it is by pointing at it. What do I have to do to that monkey to make monkey point at it? Make monkey a pointer. So instead of monkey being a single character, monkey is now going to be a pointer. So it's going to take up 4 bytes in a 32-bit machine. It's going to be a pointer. It's going to, I want it to point down there. That's where I want it to point. Just point at this space down there. So the way I'm going to do that is I'm going to say monkey equals char star in parentheses malloc. 256. Why did I do that char star there before the malloc? It's a typecast, but why? So if some people don't know what a typecast is yet. We'll explain what that is in a second as well. Why did I do a typecast?
Otherwise you could try to assign a void to
Right. Malloc returns a void star. Monkey is a char star. I can't assign a void star to a char star, so I have to typecast. In Java, you can assign subclasses to their parent variable types. But you can't say, in Java, you can't say, hey, this integer, I guess it's the course already. You can't say that this car, let's say you make a car class in Java, and you instantiate a car, you can't say int C equals car. That's a car object. You can't do that in Java. Right? C absolutely lets you do that. C doesn't care. C's like, oh, well, the compiler will be like, that's a car and that's a, like, so let's say we have a type car W, let's say this one. So we say W, it says, hey, W is not an integer, you can't do that. If you do this like so, with the parentheses around the type, what C does is like, well, that's not what I thought it was, but go for it. That is now an integer. Right? It's like, okay, it just does it. And let's suppose that the car takes up 10 bytes of space. How big is an integer? 4 bytes. So what ends up happening is, when we do this integer, it goes, all right, I'll just take the first 4 bytes and stick it in this variable over here. That's what it does. The rest of those bytes are lost. Works for me. So in this case here, the malloc returns the void star. The compiler would be like, the void and char star, we can't, those aren't the same thing. We say, no, it's going to be a char star. And C's like, okay, I don't know what you're doing with that memory. You just told me what you're doing with that memory. That's our responsibility. So now monkey is pointing to that guy down there. Now I can use my scanf with my monkey inside here. Now monkey will be that spot. We do our scanf. When they type in the characters will go down here in the dynamically allocated area. What happens when main finishes now? What happens to the stack?
Removes.
The stack gets popped off, right? So the stack gets popped off. Did that go away?
No.
The dynamically allocated memory does not go away. What's this called? But now it's a memory leak. What if I wanted to allocate another section of pink in there? All right, I got one there, maybe one more down there. What if I allocate 2 more sections of pink memory? What if I try to allocate a third? I'm out of space, my program will crash. This is called a memory leak. Because Java does memory management for you, Java keeps track of like, oh, all your pointers disappeared. I'll go and erase this for you so you can use it again. C doesn't do that for you. C goes, I don't know, maybe you're using that somewhere else. I don't know what you're doing with that monkey. Maybe you want to delete it. Maybe you want that memory to be there forever. I don't know. So the end of it is after we do a malloc, we also have to free. Which means we are going to free the pointer we created. If we attempt to free something that we didn't malloc, our program will crash. And the compiler doesn't know. I could ask it to free anything. I could say, hey, free main. The compiler will be like, I don't know if you can do that, but I'll try. And then your program will crash because it can't free main. So in this case here, I would end this with a free the monkey. For limited time only.
So is that after the bracket's closed?
So that would be, no, would be the same. Whenever you're done using the memory, you have to free it inside of whatever program you're using. Yes?
Wait, what's the star again?
So the star has different meanings at different times. In this case here, char star, and the char star here means that we're declaring a section or variable or a point that is going to be a pointer. That means that monkey here is a pointer. It is not data itself, it is a pointer to data. When we do the malloc, we're allocating place for data. So we get a location of data, not a place to be. Monkey points at data, so now monkey is going to be pointing at the data we allocate. Which one now? Correct. So before we did the char buff, now we're doing with the char star monkey, we no longer need the char buff. This is now, this program here is almost identical to the program we started with, except for now our memory is allocated down here instead of on the stack. That's a good question. Why do we want that? It's a difficult question to answer in the beginning. It is longer. The answer is, again, sharing. When you get to object-oriented programming, let's suppose you write a function that creates an object and then passes that object back to another function. Right? I want to be able to give this object to another function. If I don't have dynamic memory allocation, the memory will be freed when my function ends. Okay? So let's do this, an explicit example of this. All right. So we have our main function, and what we're going to do with our main function is we are going to write another function that does the username acquisition for us. So we're going to have a function, so what we're going to do is we're going to say, we're going to be able to do something like this. Printf percent s get name parentheses. So what I'm going to do on the right hand side over here we go to the whiteboard on the right hand side, is we're going to write the getName function. Right? So getName is going to return the user's name. Go ahead, let's write the getName function. I want you to write the getName function using the methodology that we used the first time. So the way we did it for the first assignment with the character array, the char buff with the 256. Go ahead and write that function. See if you can figure out how you want to write it. So I have the template for it here, but there's going to be some things that I'm missing. I'm missing two parts here. What are the two parts that I'm missing?
It's gonna be returned.
So I'm not using malloc yet. We're going to use malloc. We're going to do it with the buff first, and we're going to do the malloc with the second one, but not the malloc part. Still missing two things. Even if I had malloc.
The return type.
The return type and the return statement itself. What I'm actually going to return. Do I know these two things? I do. What does getName return?
String.
It returns a string. What is a string in C?
Character.
It's a character array, right? Character array is a character pointer. They're identical. They're not quite identical, but they're close enough that we can say they're identical. So we're going to return that character pointer. Which character array do I have here in my getName? Buff, right? So what I'm returning, I'm going to return buff. What's up? Where is buff allocated when I call getName?
Stack.
On the stack. Oh, that's the stack. I want to say buff. Right there, buff. And so it's growing up like that. I scan F, so they type in Scott, and Scott shows up inside the buffer here. And then I return buff, and so when I'm returning buff, I'm returning char star. What's the char star mean again?
Alright.
The pointer returns the address of. So let's say that this address is 00003798, right? Let's suppose that's the address. I'm returning 003798 there. What happens when getName finishes? The stack goes away, right? And what am I trying to print here? 3798. Is buffer at 3798? No. We may be lucky, and buffer may still have the value that we had in there before when we did this. But and this is just an artifact of buffer being of us being lucky that buff was still technically there. When we erase it, do we actively go and put zeros there? No. Why wouldn't we actively go put zeros there? Waste of CPU time. So really what's here is whatever was typed there is left there. This is the reason why so this is just left there. I call another function. Hey, the stack goes up again. What's there?
Garbage.
Whatever was there before. Whatever was there before is garbage for whatever comparatively to whatever we're going to be doing now. Or using now. So that's where garbage comes from. It's just we just leave data wherever we want. We're very messy when we program. We're like, I don't need to pick that up. Leave it there, and then I have to pick it up again before I use it. And so we might get lucky in that our data might be unmolested and might still be there. We might not get lucky and it might not work. But in general, we're going to say it's not there because we don't want to rely on luck for our programs. This is the reason why we can't use this char buff there. What's the solution in this case?
Allocate memory.
Allocate some memory, or dynamic memory allocation, so we can use. I'll use the same char buff again, but I'll use it as a pointer instead. Char star buff. Buff equals char star malloc with 256 bytes inside of it. Like so. Now when we write our program this way, what gets put on the stack? So the function, the variables for getName, right? What gets put on it? A pointer, which is just a single guy, which is buff. And it's going to be pointing at a location that the malloc creates. down here. The user types in the user information here. What is the value of buff now? The address. So let's say this address down here is 0000 A130 down there. We return buff, we return A130. Buff goes away, but we've returned A130 back to here. Is A130 pointing at valid memory?
Yes.
Yes. It points at this green section, which is still valid. I have not freed it, it has not gone away, and so this scanf, the printf will continue to work. It'll print out the correct thing. What's wrong with this, though, or what's potentially dangerous with this? Memory leak. I have not gotten rid of this here. How do I make this not memory leak? You want to free it. So let's go and free. So I'm going to free, I guess I'm going to free 000000 A130, right? Because I know that. Do I know that? I made that up. I don't know. I pulled that out of my ass. I have no idea where that memory went. When you do malloc, you don't know where it came from. You just know that you have memory. If malloc fails, your program's going to crash because you're on a RAM. But malloc fails, you have worse problems. I don't want to have to think about where my memory is allocated. What do I do?
Assign or get name variable or punch free variable.
I'm going to call this buff as well. I'm going to call get name here. I can write buff inside of all these. And that's how it works. Yes. This one here? Either. Both. Either. Not both. Either. Yes.
Is there ever any time you want to free it?
So, maybe. Maybe is the answer. You might want to free buff over here if you're done with buff. Am I done with buff here? I'm not, so I can't free it until I'm done with it. This creates kind of a problem. How do I know that I have to free the thing that comes out of get name? There's two ways I can know this. So I can look at the return type, char star, and because it's a pointer, I might think I'm going to have to free that, right? That's one way. Really, the way those what you just said there is let's look at the return type, and also I have to look at the fact that I'm mallocing some space here. What if getName took a character pointer and it returned the same character pointer? We don't necessarily know that's not what's happening. We actually have to read the code and see that there's a malloc that doesn't have a free. Is that really what I want to do for all my C programs that I'm going to be using? Now, what am I going to really want to do? What's the right answer in this case? I think we don't have. No. God, if there was, that'd be awful. You have no idea what you wanted to keep or not. Most of the time, that'd be a terrible way to do it. How do we know that getName returns something I'm going to have to free? I could. What is that called when you do that? That's it. Somebody said it. Documenting. Documentation. Do I have any documentation here? No, I don't have any comments. I don't have any function comments that tell me, hey, this getName returns something you're going to have to free. Right? If the documentation said, this function returns memory that you must free, Now I don't have to read the rest of that function to know whether or not I have to free that memory. I just get to use it. Documentation tells you. If the documentation, or you write programs where the documentation doesn't tell you if you have to free the return result, it's a problem. Because then you're just going to end up with memory leaks all over the place. One of the things that I noticed, so I know there are some of you that are still there, and I still don't fucking get what a pointer is. I still don't understand. What's a pointer? There are two, so there's, okay, so let me take a step back. There's only one kind of thing in programs, and that's data. There is data, and there are functions that operate on data. That's all that exists. Every single programming language that we use, every single programming language that you will ever think about, every single program that you will ever write is either data and functions that operate on that data. That's all that exists. So we have data. We can either refer to data by name, which is what variables are. When I say, have the code written, when I say int x, what I'm doing is I'm telling the compiler I want 4 bytes that are going to be interpreted as an integer. And I am going to call those 4 bytes x. So I'm referring to that data by name. When we talk about data inside of the memory here, let's suppose I say int x. That means that I have x right there. And that's those 4 bytes of data that are x. What else does x have? It also has a memory address. It also has a location. So x is both a piece of data, which is an integer, and it has a location. A pointer is a piece of data that is a location that also has a location. Right? Now I know, and this is one of those things that is a little strange. So when I say int star y, what I mean is that there is a piece of data named y. The data inside of this y is a pointer to something else. It is an address. It also has an address. The address of x in this case is 3204. The address of y is 3200. The data inside of x is an integer value. The data inside of y is a pointer to something else. So as an example, the value of x is 7. Because the data inside of the value here is 7. The value of y is 00003204 in hexadecimal. Because y is a pointer. What is y pointing at?
X.
X. So if I can also say, so for me to do this, the code that allows me to do this is I say y equals ampersand x. Ampersand means give me the address of this variable. So the variable of the address of x is 3204. That's what that instruction says. Y is a pointer, so it means that its value will be an address. The value of y becomes the address of x. If I want to get the value of 7 out of y, I use star y with parentheses. You don't have to use parentheses, but I'm going to teach you guys to use parentheses to start because we'll learn how to use parentheses a little bit better as we go. So star y with parentheses around it means don't look at the value of y. It means follow that pointer. So it goes, follow that pointer. What is that value? That is the value of 7. This whole thing is the value of 7. That also has the value of 7. Star y equals x in this case here. Those are identical. Because they are identical, they are the identical piece of data.
So the first one was just pointing at 3204, not the first one, that one.
The value of y becomes the address of x. The address of x is 3204. That's why the value of y is that value. I know that's complicated. Pointers are addresses that have addresses. Values are data or integers or characters that have addresses as well. We'll talk about it more. There'll be a point in time where the switch will just click and you'll be like, that was easy. I didn't